Actually, that is, R1 is connected to a 1.0 network segment. You can simulate it as a PC. Anyway, the future flow will go like this. So we have many ways to verify. Okay. Enter the 00 interface. It is IP NAT inside. We are now configured. Now if configured like this, do you think it will work? Whether it can pass or not. We have a configuration that did not do. I have a default route that is not configured. I want my PC to go online now. Assuming let it go on this R1. For example, I let it ping the R1 interface. In short, this is an external address. Ping 10.0.1.2. Now, first of all, there must be a route pointing out. IP route 0.0.0.0. 0.0.0.0. A default route points to 10.0.1.2. Then let's analyze. I have done what configuration? NAT already done. The internal and external interfaces match. Then turn it into an outgoing interface. Turn with the port. This also configures. The access list matches the PC traffic. Released any. Refers to the default route. Then it stands to reason. If the PC wants to ping this interface now, just visit the R3 interface of the public network. Can it be pinged? You can think about it. I will ping now. Ping 10.0.1.2. No pass. Why didn't it work? Is there a problem with our configuration? Okay. We need to enter the subinterface. If you configure the subinterface here in the future, then actually, when you are going to configure the internal network interface, you have to enter the subinterface instead of the physical interface. When we typed inside just now, it is input under the 00 interface. But you don't need to cancel this order. You can go directly to the internal network interface. Interface E00.10. IP NAT inside. Go to 00.20. IP NAT inside. This is the configuration. After configuration, we also go back to PC1. Let's ping again. It works. The reason why I will tell you about the combination of one-arm routing. Just to draw your attention to this. Which interface address configuration takes effect? Actually, you need to configure it accordingly. Let's try it here on PC2. Ping 10.0.1.2. Okay. Also works. That is equivalent to the first two steps and we are done. PC1 automatically obtains the address. PC2 manually configures the address. Get fixed address. Configure subinterface. And then do address translation. Realize that the address of the Internet private network can communicate with the outside world. That's all we've done. We can also verify. Show IP NAT translation. We just sent a lot of pings. Then here you will find 2.2 there are 5 ICMP packets sent out. Local 5 mapping entries. Each time is a random high port locally. A port mapped to the outside world at 10.0.1.1. This is for PC2. The above 5 data packets belong to PC1. A total of 10 packets. Because each is pinged 5 times. Each is 5 ports. So our daily communication consumes a lot of ports. Everyone should know this. Let's go on to configure. Next is OSPF. Now the static line of the whole network has been configured. Configured on the gateway. Pointed to a static route out. Therefore, we cannot configure static access to the external network. It is impossible to write a static point to the private network. This can only be used on the default route. Now PC1 and PC2 can ping the addresses on the public network. That's like being able to go online. Let's start to do OSPF. Enter OSPF configuration mode. Router OSPF. Let's say this is 100. Then press enter. We configure the complete. Router ID 1.1.1.1 will be configured like this. In dotted decimal. Then declare. Network 14.1.1.0. 0.0.0.255. Declare into area 0. R1 also declares network segment 13. Network 13.1.1.0. 0.0.0.255. Area 0. The last one announces the loopback address. Network 1.1.1.1. R2 is the same. Router OSPF 100. Router ID 2.2.2.2. Then we start the declaration here. Network 24.1.1.0. This is the anti-mask. This is not a wild card. Network 23.1.1.0. Last one. Network 2.2.2.2. We then configure. Router ID 3.3.3.3. Then we declare. This announcement is less. Network 13.1.1.0. Network 23.1.1.0. This is the last device. Router OSPF 100. Router ID 4.4.4.4. Network 14.1.1.0. Network 24.1.1.0. Okay. We are done with this configuration. Let's give it a little time to learn now. I think I should have learned almost. Let's look at the routing table. Show IP route. Let's take a look. Now R1, R2, R3, R4 enables OSPF and is done. 1.1 can tell NAT 2.2 but not ping 2.2. The loopback port on R1 can tell NAT the loopback port on R2. But can't ping. Let's do this last configuration. Let's do this routing first. PC access 2.2 goes down when it goes. Walk up when you come back. This is not easy to verify. We only need to modify the corresponding path. We can look at its routing table on R1. In short, no matter whose traffic goes to R1, R1 must look up the table and forward. Just go to visit 2.2 now. Data here. In fact, it looks at its watch. So it looks at the current table. When going to 2.2, do you go down or up? When including future reply packets, does it go up or down? We are now on R1 to see. It goes 2.2 both up and down. It's loaded. Now there are two lines. Then we will continue to check on R2. Show IP route. For R2, going to 1.1 also loads. If it goes to 2.2 in the future, it is not sure that it can go down. It's loaded. So for now, it can't be sure to go down. Then you can't go back. Because it can be seen from this that R1 is also 2. So we're going to modify. Influence their routing. Modify cost. We talked about how OSPF affects routing. Let's review again. I want R1 to go down to 2.2 now. So let's take a look at how its cost is calculated. This 110 is its administrative distance. We won't talk about this. How did this 21 come out? The default cost of a loopback port address on R2 is 1. Like walking here. Inbound direction of route convergence. This interface is 10. This interface is 10. In Cisco. By default this is a 10M interface. Then its cost is 10. So it is 21 calculated from 1 plus 10 plus 10. If we want to influence routing now, we sure want it to go down when it goes. That is. Next hop is 13. I have to increase the cost on the road of 14.1.1.4. Make it greater than 21. I told you when I was calculating. We need to change the loopback port. We will not change the loopback port today. Let's change the physical port. Because it was shown before. Let's demonstrate a different. Usually, we changed the loopback port on the project to be more. But the future is not certain. If OSPF has many paths at the same time, all want to access this loopback port. If you modify it, it will also affect many roads. To be honest. In fact, it doesn't matter which one you change. Let's change the physical port first. I wish I went down now. Increase the cost above. So which interface can I change? Let's just pick an interface. Since I said it, this is a loopback port. Then this interface and this interface. Let's change the device in the middle. For example, I changed the interface of R4 to a larger size. Because routing is converged like this. So it goes under this interface.